Hello, this is Jack Jackson. This is the first of a series of lectures on quadratic relations. So we'll start with an introduction here. Quadratic functions have the form f of x equals ax squared plus bx plus c for some constants a, b, and c. So they're second degree polynomial equations. We'll see a little bit later on as we go through these notes that they have three really good forms that we might look at. One is called the general form, p of x equals ax squared plus bx plus c. And from this one you can see that 0c is the y-intercept. They also turn out to always have a standard form, which is p of x equals a times x minus h squared plus k. And from this form you can see that they're just transformations of the basic power function y equals x squared. And so this has the vertex hk. And there also can be written in factored form. You can always do this if you allow r1 and r2 to be complex numbers. But if r1 and r2 are real numbers, then these things correspond to the x-intercepts, r1, 0 and r2, 0, if they're real numbers. But there's a factored version there. So we're going to investigate what each one of these things tells us about quadratics, and along the way we'll be doing several different things. Now first I'm going to review a few basics for some operations with polynomials in general, specifically with binomials, but also with polynomials. It turns out that polynomial arithmetic is very similar to just integer arithmetic. So one of the most basic things that we've studied earlier is the distributive property. We talked about this way back in our first unit. And a times parentheses x plus y close parentheses is a times x plus a times y. Okay, and so that's a distributive property. So if we use this property left to right, that's called expanding or multiplying out. So here's some examples. 3 times parentheses 2x plus 4 is 3 times 2x, which is 6x, plus 3 times 4, which is 12. So it's 6x plus 12. 3x times 4x minus 7 is 3x times 4x, which is 3 times 4 is 12, x times x is x squared. 3x times negative 7 is negative 21x. And if you just have a negative outside of a parentheses, that's like a negative 1 times that parentheses. You distribute that and it becomes, in this case, negative 4x plus 7. Throughout these notes you're going to see some exercises for you to try that are matched exercises. Please go ahead and try to work those yourself. Now, we had talked earlier about the algorithm that we use to multiply two two-digit numbers. And it's basically a repeated application of the distributive property. It gives us the four different products to look at. Well, we can use this exact same algorithm to determine the product of binomials, and it's often referred to by the anagram FOIL. F means first term times first term. O means the product of the outer terms. The I is the product of the inner terms, and L is the product of the last term. So put that into play here. 3x plus 2 times 2x plus 4. First times first gives you 3x times 2x, which is 6x squared. That's the F. The O is the outer two, the 3x times the 4, which is 12x. The I stands for multiply the inner two, 2 times 2x, which is 4x. And the L is the last times last, 2 times 4 is 8. Now what usually happens here on products of binomials is oftentimes those middle two terms are like terms and we can combine them. 12x plus 4x is 16x. Of course when we're doing that we're actually using the distributive property again by factoring out the x and then adding the coefficients. 12 plus 4 is 16. So let's do a couple more examples here. 3x minus 5 times 4x plus 8. First, the F, 3x times 4x, 12x squared. The O, 3x times 8 is 24x. The I, negative 5 times 4x is negative 20x. And the L, negative 5 times 8 is negative 40. Combine like terms in the middle, you get 4x for the middle. So oftentimes you'll end up with well, you get 4 terms, a quadrinomial, all the time, an f, o, I, and l, anytime you multiply 2 binomials. But oftentimes the middle terms will combine until you end up with a trinomial. So when you take 4x minus 7 squared, that's 4x minus 7 times 4x minus 7. So the f is 4x times 4x, 16x squared, which is the 4x squared. And you got the L, negative 7 times negative 7, which is negative 7 squared, which is 49. Okay? However, it's not just a minus b squared is not just a squared plus b squared or a squared minus b squared. You get a middle term as well. And you get that, notice both the o and the I are 4x times negative 7, which is negative 28x. And so they actually don't cancel out, they actually double up, and you get negative 56x. Turns out what happens to get it to cancel out in the middle is what's called a sum and difference pattern. 3x minus 5 times 3x plus 5. When you do this, the f is 3x times 3x is 9x squared. The negative 5 times 5 is negative 25, so that's the 3x squared minus the 5 squared. And then notice this time, one of the outer product is 15x and the inner product is negative 5x, negative 15x, and so they cancel out. So this gives us a couple of special products that if you take in general a plus b and square it, you do get a squared plus b squared, but you also get 2ab in the middle. But if you take we could call that a binomial squared, and the answer on the right is called a trinomial square. The one that has the o and the I opposites that cancel each other out is called a sum and difference pattern on the left, where we have a plus b times a minus b, and the answer is a difference of 2 squares, a squared minus b squared. So here's some practice problems to practice multiplying out. And notice again, this algorithm is really just the same algorithm we use for multiplying two two-digit numbers. Now what about factoring? Well, we can factor quadratics over the integers. This goes backwards from multiplying out. So it's exactly backwards from what we were just doing. Okay, so basically in multiplying out, if you look here in these problems, let's say one of these back here, let's say D here. What do we have? We have basically the left expression is basically a times b. A binomial times another binomial. So it's basically the last operation there is multiplication. But if you look at the answer is basically 2 terms added or subtracted together. Okay, so we can go the other direction though. We can start with something that's basically added together, and then from there break it down into 2 or more things multiplied together. So the first thing we can do is called common factor or distributive property factoring, where we start with the ax plus the ay, and we write that as a times x plus y. And we've already seen our other special products we can write backwards. The difference of 2 squares, a squared minus b squared, we see comes from a plus b times a minus b. And if you have a squared plus 2ab plus b squared, that's going to be a plus b squared. And if you got a squared minus 2ab plus b squared, that's a minus b squared. And then we can do what's called trial and error or anti-FOIL factoring, where we just go backwards from FOIL. And we'll talk about that a little bit more as we go. So these are the most basic ones that we use for factoring quadratic things or second-degree polynomials. But in general, when we talk about factoring of polynomials with integer coefficients, we always put the terms in decreasing order first, and we always check the patterns in the following order. So the first thing we do is check for common factor or distributive property factoring. So in all of these factoring patterns, there's a pattern of the problem and a pattern for the answer. In this one, the pattern of the problem could be that any number of terms, but what we do is we find the greatest common factor of each of the terms of the polynomial, and then we include that greatest common factor, okay, including the greatest common factor of the coefficients and the variable parts. And so we factor out this greatest common factor. So basically, we go through here and we get the largest power that we see on that occurs everywhere, okay, on either a prime number base or a variable base. So if you notice, all of these have a 2 square or a 4 that we can factor out. They all have an x and all have a y in this example right here on the right. So we can take the 4xy and factor that out. Well, the opposite of the distributive property in this direction, I should say, is in the other direction it would be multiplying, so in this direction it's dividing. So we take the 12x squared y and divide it by the 4xy. So 12 divided by 4 is 3, x squared divided by x is x, and y divided by y is 1, so you get 3x here. Then we have negative 4 divided by 4 is negative 1. There's our coefficient. The x's cancel out, and y squared divided by y is y. And of course 8 divided by 4 is 2, and then the xy's cancel completely, and so we see the answer is 4xy times parentheses 3x minus y plus 2. Notice that if the original has 3 terms, the thing in the parentheses will also have 3 terms. It'll have the same amount of terms as the original did, and you'll have a monomial 1 term out front. Okay, so always when you're factoring, check for a common factor first. Get that factored out all the way. Now the next thing is we want to check for difference of 2 squares. It's important that you check for these patterns in this order. So what's the pattern of the problem? It's got to be a difference of 2 squares. So it must be a binomial, it must be a difference, and the 2 terms must be perfect squares. In other words, can you write it as something squared minus something else squared, an a squared minus b squared? If you can do it, then the answer is whatever's in the first parentheses plus whatever's in the second parentheses, and then the same thing with the minus. So, for example, so the basic pattern is x squared minus y squared equals x plus y times x minus y. So, for example, 16x to the 6th minus 9y squared. First, notice that it's in decreasing order, and notice that it doesn't have any common factors, so we always check that first. Next we see is a difference of 2 squares. So the question is, can you write it as parentheses square minus parentheses square with the right thing, something in the parentheses? And the answer is yes. 16 is 4 square, x to the 6th is x to the 3rd square. 9 is 3 square, and y square is, of course, y square. So the first term is 4x cubed squared, and the second term is 3y squared, and we have a difference in the middle, so in fact it does fit the pattern of the problem. So the pattern of the answer is you simply bring the 4x cubed down, bring the 3y down, put it with a plus, and then repeat the same factor with a minus instead. A trinomial square is the next pattern. So if it's not a difference of 2 squares, it could be a trinomial square, perhaps. Well, so you check that next. A trinomial square is squaring a binomial in reverse. So the problem is a trinomial with the first and last terms positive and they're perfect squares. In addition, the middle term works out to be twice the product of the square roots of the first and last terms. So basically we want to see if it's something plus or minus something and then the whole binomial squared, which is what the answer would be. So we first check to see it's a trial and error, and the first and last terms have to be positive, so we check that first. Then we look, is the first one something square and the last one something square? Yeah. So we bring that down. The first one's the square of 2x. I usually won't write out this middle term. So the first one's 4x squared is the square of 2x, so I bring 2x down. The last one's 9, which is the square of 3, and the sign in the middle is going to be the sign in the middle is going to come down. So, we bring the 2x here, the 9 here, and that sign in the middle goes here. But then the question is, does the middle term work out right? And to check the middle term, this may or may not work. But for squaring it, remember, we've got the first and last part right. Square 2x, you get 4x squared. Square negative 3, you get positive 9. Now, if it's going to work, the middle's got to be twice the product, so you just have to check it. It's a little bit of trial and error here. So 2x times negative 3 is negative 6x, and double it is negative 12x, and so it does check. Okay, now this is a little harder to explain. Trial and error are anti-FOIL. Now, not every problem will factor. So some trinomials will not factor if we're only allowing natural or integer coefficients. So we start with integer coefficients, and we're only going to allow integer coefficients in our answer. Okay? Now, actually, whether something will factor or not depends on what you allow for coefficients. Some things that will factor, say, over the integers or the rational numbers, but there are some things that won't factor there. But if you allow, say, irrational numbers, then they will factor. Okay, I'll come back to this idea. Well, let's just do it now. Let's talk about this a little bit right at the moment. So if I take something like x squared minus 4, that factors as x plus 2 and x minus 2. So that factors just fine if I allow integers. So we would say that factors over the integers. But if we took something like x squared minus 5, if we're talking about factoring over the integers, we would say this is a prime polynomial or an irreducible polynomial. And like a prime number, you can't factor it down any further. However, if we allow ourselves to change what we allow for coefficients, we could write it as x plus the square root of 5 times x minus the square root of 5. So it's a prime number if we are prime factor. It's a prime polynomial if we only allow natural number or integers for coefficients. But if we allow irrational numbers, well, any real number, then it is not a prime number. You can factor it. Then you've got something simple like this, x squared plus 1. If you allow only integers for the coefficients, it is irreducible, prime factor. It cannot be factored down any further. Even if you allow real number for the coefficients, it can't factor anymore. But if you allow complex numbers, you can factor it as 1 plus the imaginary number, or x plus the imaginary number I, x minus the imaginary number I. See, notice this is x squared minus I squared. I squared is negative 1. And x squared minus negative 1 is x squared plus 1. So it does factor if you allow complex numbers. So this one factors over the complex, this one factors over the reals, this one up here factors over the integers. This one, x squared minus 5, is prime if we only allow integers for coefficients, but it's not prime if we allow real coefficients. X squared plus 1 is prime if we allow integer coefficients only. It's prime if we allow real coefficients only. But if we allow complex coefficients, it's not prime. It can be factored down. So right at the moment over here in the factoring, I'm talking about factoring only with integer coefficients. So in that case, some trinomials cannot be factored if we only allow integer coefficients. Okay? Now, here's the basic idea. You basically get the f to work. Actually, that's not the L to work here and the f to work here from FOIL. So remember, the FOIL is first times first has to be 12x squared. So what are our possibilities? We could have 12x times x, 6x times 2x, or 4x times 3x. So we've listed all the possibilities to make the f work of FOIL. Now what are our possibilities for L? Last times last will be this last coefficient, the constant term. And what are our possibilities? Well, 1 times 90, 1 positive, 1 negative. 2 and 45, 1 positive, 1 negative. 3 and 30, 5 and 18, 6 and 15, 9 and 10 are all the pairs of factors with integers. Again, we're only choosing integers so that we get that to work out. Now, the rest, this is actually 72 possible combinations because you got to take each one of these. And, for example, you could put the 1 here, and the negative 90 here. We could put the negative 90 here, and the 1 here, and so forth. And we have lots of different possibilities there to try. And at this point becomes a guess and check or trial and error, and you just have to pick one of these and see if you can get the middle to work out. The only way you can tell if it's prime, where it will not factor at all, is to try all 72 different combinations and eliminate them. Now, some things you can also use. You can kind of eliminate quickly. For example, I know I can't put 3 here, because here, if a 3 would go here, it means I could factor out a 3, and I'm going to make sure that I've gotten all of the common factors out first. That's why we do that first. So some things I can do without even checking the middle term. So 3 and 30, I can't put 3 or 30 in either one of these because I can't put 3 or 30 here. I can't put a 3 or a 30 here. I can't put a 3 or a 30 here, so I can cancel those out right away. Okay? So it takes a little practice at this, but you can actually work this out, and with a little trial and error you can do it. And the one that actually turned out to work was -9 and +10. This is the one that worked. And let's do the FOIL. First times first is 12x squared. Last times last is -90. We know that's going to work. And here we get -27x and +40x, which combines to give us 13x, which is what we had there, so that does check. So always check it to each factor. Now check each factor to see if it can be factored again. If a factor cannot factor anymore, it's called prime or irreducible, just like we call it when you can't factor a constant anymore. A whole number anymore. So let's look at some examples. X squared plus 7x plus 12. It's in decreasing order. There's no common factor. X squared at the first, just a 1 there, so it's got to be 1x and 1x for the first. The last could be 1 and 12, 2 and 6, 3 and 4. The signs have to both be positive or both negative. Middle term's positive, so they're both positive. And we need something that's going to add up to 7. 3 and 4 is going to be the one that works. The next one, c squared plus 7c minus 30. Again, just a c squared, so you get a c and a c. 30, we've got several possibilities. What are they? There, of course, there's 1 and 30, 2 and 15, 3 and 10, 5 and 6. And this time this is negative, so we're going to get 1 positive and 1 negative. And we want them to be 7, so basically the difference has to be 7. So 3 and 10 turns out to be the one that works. You can check that out. C times c is c squared. 10 times -3 is -30. -10c minus 3c is 7c there. And so forth. And we can try these out. Let's see the next one. 5x squared plus 17xy minus 12y squared. We're going to split the x's and y's up, so it's each one has got an x and a y term. 5x squared, only way we're going to get that to work out is going to be 5x and x. We got several possibilities for the 12y squared. We got to split the two y's up, but we can do 1 and 12, 2 and 6, 3 and 4. Turns out 3 and 4 is the one that works if you get the signs like they are here. If you ever do 1 and you get the signs, you get exactly the opposite of the middle. Just switch your two signs and then it'll work out. So 5x times x is 5x squared. Here we get -12y squared. And then check it, the middle term. -3xy plus 20xy is 17xy. This one here, we could do it in stages. We first factor out an x squared, leaving us 3x squared plus 17x minus 28. And then we'd factor that with our trial and error, x and 3x, and it turns out 7 and 4 gives us 28, 1 positive, 1 negative, and we put the signs this way. I believe the middle term will work out right. 21x minus 4x is 17x. This next one is a difference, actually of fourth powers, but it's a difference of two squares. So we can think of it as x squared minus 4 squared. So that's x squared plus 4 times x squared minus 4. The first one is prime if we're only allowing integers for the coefficients. But x squared minus 4 is x squared minus 2 squared, so that's x plus 2 times x minus 2. The next one factors as the a to the fourth. To get the a squared in the middle, we're going to break up the a's to be a squared and a squared and a squared. And then for the 20, we've got to try either 1 and 20, 2 and 10, or 4 and 5. And since this is a positive sign here, that means they're both going to be the same sign, and they'll be the same sign as the middle term, so they're both negatives here and here. So to get 9 in the middle, we need a 5 and a 4. So that'll be that works out that way. A squared minus 5 will not factor over the integers. It will factor over the real numbers, but not the integers. This x squared plus 4 will not factor over the integers or the real numbers, but it will factor over the complex numbers. But the a squared minus 4 is a squared minus 2 squared, so that'll factor on down. So notice that a sum of two squares won't factor over the natural numbers. A difference of two things here will only factor if they're both perfect squares, at least in terms of factoring over the integers. The next one is a difference of two squares. The next one, I rewrite it in decreasing order first, negative 40x plus 5, then factor out, if this first term is negative, we always factor a negative out here, and we have a common factor of 40 and 5. The greatest common divisor of both of those is 5, so it's negative 5 is factored out, and the rest is 8x minus 1, which won't factor any further. Finally, the last one here is a trinomial square. It's in decreasing order. There's no common factor. Okay, so 4x squared is the square of 2x. 81 is the square of 9. The middle sign is negative. And then we just need to check the middle term and see if it'll work with the square there. If not, we'll go to the trial and error method and see if anything works. But the middle term does work out just like this, because you multiply these, you get negative 18x, and then you double it, and that becomes negative 36x. So that does work out. And here's a lot of good practice problems for you to practice. Next, we're going to review solving equations by factoring. So all of this stuff is a review of, well, basically Algebra 1 stuff that's covered in beginning algebra or intermediate algebra at the college level. So one important fact is that when product of two numbers is 0, one of the two numbers must be 0. We've used this before in the course. So if a times b equals 0, that happens if and only if a equals 0 or b equals 0. Now notice this is a very special property that 0 has. For example, if you have a product of two numbers is 12, they could certainly be, one of them could be 12, it could be 1 and 12, but it could just as easily be 2 and 6, 3 and 4, or even 24 and 1/2. It doesn't have to be. So the only thing that guarantees that you're going to have one of the two numbers be the same there is 0. So when we find some terminology here, when we talk about solutions to an equation, they're sometimes called roots of the polynomial or zeros of the polynomial. So roots or zeros are x values that will make the polynomial equal to 0. So for example, if I have this factored here, x plus 1 times x plus 3 equals 0, that says that that's true if and only if x plus 1 equals 0 or x plus 3 equals 0. But x plus 1 equals 0 means x equals negative 1. And x plus 3 equals 0 says x equals negative 3. In fact, you can probably do this in your head. Just look at this and see that x is negative 1 and x is negative 3 are the solutions. So if you're just looking at this left side as a polynomial, then we say that this negative 1 and negative 3 are roots of that polynomial, or zeros of that polynomial. If you're talking about this whole equation as an equation, then we say that these x's are solutions to that equation. If you're taking the polynomial and graphing it, like f of x equals x plus 1 and x plus 3, then these are going to be x-intercepts where the graph crosses the x-axis at negative 1 and negative 3. So they correspond to x-intercepts of that function. By the way, by multiplying this out, we get x squared plus 1x plus 3x, that's plus 4x. 3 times 1 is 3. Notice here, this tells you that the y-intercept is 0, 3. Because if you plug in 0 here, you can see these clearly go away. and you're just left with 3. So, the graph's going to look something like this. So, the next step is to solve some quadratic equations, but we're going to use the factoring method. So, get 0 on one side, and then factor the other side. So, we write this as x squared minus x equals 0. Using common factor or distributive property factoring, we'll factor out an x. So, that's x times x minus 1 equals 0. So, x minus 1 equals 0, or x equals 0. So, it says x equals 1 or x equals 0. You can write it this way with the word or you can write it this way: x is an element of this set. Positive 1, sorry. And 0. So you can write it this way or this way. When there's only two things, it's about the same difference either way. If there's one, I think it's easier to say, for example, x equals 4 than it is to say x is an element of the set containing 4. I'd prefer this way. If you've got 3 or 4 things like x equals 6 or x equals 5 or x equals 8, I think it's easier to say x is an element of the set 6, 5, 8. It's a little bit easier to write this way. And this way it's about the same either direction. Okay. Okay, moving along here. Where are we? X squared minus 4. Well, that factors as a difference of two squares, so that's x plus 2 times x minus 2. X plus 2 equals 0, or x minus 2 equals 0, so x equals negative 2, or x equals positive 2. Of course, you can check these by plugging them back into the original equation, as we could with solving any equation. X squared minus 3x minus 4 equals 0. That factors with the trial and error or anti-FOIL factoring as x minus 4 times x plus 1. Check it by doing the FOIL. Okay, and then that means either x is 4 or x is negative 1. The next one, 12x squared minus 23x plus 10. So they're getting a little harder to factor, but still not too difficult. There were several choices for the first. Could be 12x and 1x, 6x and 2x, or 4x and 3x. For the last times last, we have several possibilities that we may need to check, including 1 and 10, 2 and 5, well, I guess 1 and 10 or 2 and 5. Although they're both, since this is positive, these are both signs will be the same, and they'll be the same as the middle, so both of these signs will be negative here. Alright, well, which one works? The one that I have here does. 4x, so let's check it out. 4x times 3x, that's the 12x squared. Negative 5 times negative 2 is positive 10. That's negative 15x. That's negative 8x. That adds up to negative 23x. Okay, that's good news because that's what it's supposed to be. So if we can get it factored, then we can solve it, because now each factor we set equal to 0. And then these are linear equations, pretty easy to solve. Add 5 to both sides, divide by 4. X is 5/4. Here we add 2 to both sides, divide by 3. X is 2/3. So these are our possibilities there. Another example. First I factored a 4 out. Maybe I should show this step in the middle. Then that's 6x squared minus 11x minus 35. And then the 6x squared minus 11x minus 35 further factors as 2x minus 7 and 3x plus 5. Well, notice 4 is not 0, so one of these other factors has to be the 0. So either the 2x minus 7 equals 0, so that would make x 7/2, or the 3x plus 5 equals 0, which makes x negative 5/3. Okay, I'm going to stop there. We'll pick up the video, the next video on the next part.